We'll proceed in the primitive calculus and we will see Taylor series and Maclaurin series. Very, very, very precious. As usual, calculus, you are genius. If calculus is genius, then there are many, like if you have a religion, then there are many saints. They come in religion. They support the religion, and this is how religion sustain or religion make progress. That way, when calculus came, many saints came into the field of calculus, and this is how calculus retained and calculus progressed. So, that is the scenario. In that, there is one Mr. or Sir Taylor came into the picture. Maclaurin, he also came into the picture. Marvelous, amazing, beyond belief work. Marvelous, amazing, beyond belief work. So what we have learned till now? So we have learned that for if we go for addition, then there are three ways: addition, multiplication, and then calculating the addition through area. If it is through area, then it is integral calculus. Now, if I have a function fx, integral calculus works in algebra. So area pointer point toward algebra, and then integration or something like that, the actual calculation of the area through the calculation of area through numeric way. If I want to calculate area through numeric way, width into height, that is the area. Then numeric science is all right. But if height is variable, if there is an independent component, width is independent component, and height is variable, if width is independent component and height is variable depending upon the width, independent component width, then height into width becomes logical. If width is 4 and height is 10, if height is fixed 10 and width is variable, independent component, what is the area? 10 into x. If height is 10 and width is 8, then what is the area? 10 into 8. If height is 10, width is x, any x, 10 into x. That is all right, no problem. So independent component I have taken as variable. But what about width is x, any x, but height is not constant. What is then height? If it is not constant, then what is the height? Then height is variable, is a function on x. Means you are trying to say height is algebraic equation over x. Yes, it is an algebraic function over x. If that is true, then height is variable. Can you give me one example? X. Function over x is x. X means it is a slant line. If this is x-axis, then this is constant value. If height is 10, then this is a constant value. Everywhere it is 10. But if height is function over x-axis, then it is x. X means when independent component is 0, this is also 0. As independent component is growing, the height is also growing. So this is x-axis and the function over x-axis is x. If that is the case, then this now if I want to calculate the net collection, then please watch the all previous videos. So if you want to calculate the net collection, then I have to calculate the area. So area of the triangle, it forms a triangle, and that is half of the rectangle it may form, that is now x square by 2. So we came to a conclusion that if I have polynomial equation x to the power n, then area underneath is x to the power n plus 1 divided by n plus 1. So if function fx is a polynomial equation of x to the power n, then its area integration becomes another algebraic equation fx. Integration, it brings another algebraic equation gx. Fx gx. Gx is t to the power x to the power n plus 1 divided by n plus 1. Now we saw If that is the case, if gx is integration of fx, then we can do some operation in gx and it would become fx again. From fx to gx is integration, then gx to fx is anti-integration. So that is also called derivative differentiation and whatever. So derivative or kind of uh, differential differentiation. Okay, so what we saw is that if I have a if I have width and height, I want to calculate area, then it is numeral multiplication. But height is function over independent variable, that is width, then it becomes algebraic. Algebraic multiplication, numeric multiplication is area, then algebraic multiplication is also area. But there is a way to calculate the algebraic multiplication, to calculate the area, that is integration fx to gx. Now from gx, if I want fx back, then it is called derivative or it is called differentiation. Okay, so multiplication and then division. If fx into x, fx into x, height into width is area, fx into x is gx, then gx by x is fx. Okay, so this is the relationship. So one is multiplication, I mean integration. Okay, multiplication is numeric multiplication, integration is algebraic multiplication. Numeric division is division, whereas algebraic division is differentiation. To identify it is really calculus, then fx into x is replaced by fx dx, gx by x replaced by dgx by dx, so that people understand it is algebraic division or differentiation. Gx to fx, fx to gx. Now what people saw that their final aim of the life is to find the integration of a particular algebraic equation. Calculus begins from algebra, but it ends in algebra. I mean everything is algebra. So where everything is algebra, when the height is in algebraic equation, then idea was to try to quickly find out all the integration ways. So x to the power n, people found x to the power n nothing but x to the power n plus 1 divided by n plus 1. Similar way for trigonometric function, they try to find out exponential, logarithmic, whatever, try to find out. People saw that the basic, that is the polynomial equation, if they find, then on top of it, it's a stack, and top of it they can find all the algebraic equation. This is what people saw. So any algebraic equation see on the top, keep breaking it, keep breaking it, keep breaking it, till you come to a layer where you know the integration. So this is the way people started. Another way people started is through, if gx is there, if there is any function gx for which differentiation is fx, this proves that fx integration is gx. This way also people started finding the integration. Then what is differentiation? From gx to fx, what is differentiation? People saw that if they can draw graph of fx, that is rate of collection, then they can draw graph of gx also, that is the net collection or area. If they draw graph of gx, then the aim of fx is fx into x, height into width, fx dx is gx, but aim of gx is gx by x or dgx by dx to find back the fx. So dgx by dx means in a certain interval along the independent component, how much, if this is independent component, if I take two points on the independent component, if this is independent component, I take 2 points on the independent component, x1, x2, or x and x plus delta x. At that moment, if I take this interval, and then at these two intervals there are two heights, if I subtract these two height divided by this interval, rate of change I get at x. At x I get rate of change. X can be variable, but every moment if I do height by width, where the width is only delta x constant, then the gx by x or dgx by dx is different. So dgx by dx at any moment x, what it is, that I have to find. So certainly gx to fx, again it is algebraic equation. Then as per the formula gx plus delta x minus gx to height. If this is x-axis, there is a x point. From there, I take delta x. So x plus delta x. At this, what is the height? At x, what is the height? Difference in the height divided by difference in the width. That is rate of change. So g x plus delta x, g x. If I subtract divide by delta x, that is the differentiation at that moment. So since x is variable, so it works. So gx plus delta x minus gx divided by delta x is the differentiation. Integration is calculation of the area. That is the integration. Width into height. Width is x, height is fx. Integration. When the collection is gx, dgx by dx, gx by x. Directly we cannot do gx by x. So for that, any moment if it is x, any moment at any x, gx plus delta x minus gx divided by delta x. Or if this is x-axis, at any point x I want differentiation rate of change, then I take delta x on right side and delta x on left side of the x, considering it will be now equilibrium. So f gx plus delta x minus gx minus delta x divided by 2 delta x. If that is the case, then we get the kind of fx back. Okay, so through these fundamentals, we found out the derivative of sine x, then exponential e to the power x. Now, if I want logarithmic differentiation, then I broke it into exponential and found the differentiation. If I find the differentiation of gx is fx, then for fx integration is gx. This way we continue. Okay, now when things goes up, then more things can happen. Now Taylor series, there are two ways to understand the Taylor series. What is Taylor series? What is Taylor series? Consider I have a function, I have a straight line. I have a straight line. The equation of the straight line is y equal to 10x plus 5. Y equal to 10x plus 5. What is y equal to 10x plus 5? I don't know. This is the line equation. Y equal to 10x plus 5. If this is a function fx, consider any function fx. Y means fx. Any function fx equal to any function fx equal to 10x plus 5. Can I reproduce this fx exactly as, can I have another function gx which is exactly at fx, but it needs few information from the fx. Fx, function fx or y equal to 10x plus 5. Fx, function over fx means y, function over x is nothing but, function over x is nothing but 10x plus 5. Can I have another function gx, a new function gx which is exact replica of fx, provided I need few information from the fx, not everything. Can I reproduce a fx function as another function called gx, where fx is equal to 5x plus 5? What information I need? Okay, now I have a function fx, I have another function gx. Gx is only polynomial function of a degree 1. Fx is any function, but right now I have taken only 1. So fx equal to 10x plus 5. Now, when gx is saying I want some information from you so that I can reproduce you. Now, fx is saying what information you need. I need derivative, one derivative. So, dfx by dx. dfx by dx equal to 10. Give me 10. Okay, if it is 10, then it produces a function gx equal to dy by dx into x. dy by dx into x. So gx is a new function where dy by dx is 10 into x. It is exactly same function. Only constant 5 is missing. He can ask that now I believe it's all right. Now, next question is that if this is the exact replica of it, then it asks this that, okay, so can you tell me that this line passes through which point? Any point through which this line passes through. Then it says line passes through 0 0.5, 0, comma 5. That's why it is y equal to 10x plus 5. So if it passes through 10x plus 5, 10x plus 5, it passes through, means if there is a line is tilted 5 up along the y-axis. If that is true, then it is now fx equal to 10x it has reproduced. So it will become y minus y0 plus 10x, or y equal to, or gx equal to fx gx. Gx equal to dy by dx into x. Gx equal to g at x some point. Okay. What it is trying to say, what is it trying to ask fx? So I will complete now. Okay. Now there is a function fx, there is a function gx. Now gx is saying that I can reproduce you. Can you give me differential derivative? Can you give me a kind of gradient derivative, single derivative at point A, any point A, any point A. Okay. Now fx equal to 10x plus 5. Now dfx by dx equal to 10. There is no question of a. It is a constant 10. Okay. So he is asking what a you want. Any a you want, that is the 10. Okay. He is saying no at a. A is 10. Fx gx at a, everywhere it is 10. A is 10. Now he is making a line. So he is asked for single derivative. He is making a line. Line is nothing but y minus y0 equal to dy by dx x minus x0. That is the formula of a line. If I want to make a line, so y minus y0 equal to m dy by dx x minus x0. So y equal to m x minus x0 plus y0. Y equal to m x minus x0 plus y0, where x0, y0 are any specific point through which line passes through. So anyway, now the dy by dx derivative what we have got, this derivative is a scalar value. It is not a polynomial function. Gx, fx is a function for which gx is the copy. Fx is a function for which gx is the copy. Gx wants certain information from the fx. Information it wants is, can you give me gradient, one first order gradient, first order derivative at point x equal to a. It replies that is 10. Now it knows that y minus y0 equal to dy by dx at x equal to a. At dy by dx can be algebraic function at x equal to a, x minus x0. Okay. Now it will convert as y equal to y0 plus dy by dx at x equal to a, x minus x0. Now x0 is a because at a we are interested. So y0 is nothing but g at a. Y is nothing but gx. Y is nothing but gx. Sorry, fx. I mean y is nothing but fx. So fx at x equal to a. Now gx equal to f at a plus df by dx, okay, plus dfx by dx x minus a. Fx is a function, gx is, I am trying to create exact replica. Fx is a function for which I want gx an exact replica. Gx is asking fx, can you give me first order derivative at point x equal to a? Now, if it receives, then it is making the line equation y minus y0 equal to dfx by dx, dfx by dx, x minus x0. Then y equal to y0 plus dfx by dx at dfx by dx at x equal to a, x minus a, x0 become a. So gx equal to y0, y0 change to f at a, y is nothing but vertical, f at x equal to a, fa plus df by dx, dfx by dx at x equal to a embraces x minus a. Okay, so that is the kind of this is called Taylor series approximation of fx. As can you see, I am making a polynomial equation. Now suppose that there is a kind of now fx is 10x plus 5, 10x plus 5. Now let's leave all the formality. Now fx is of order 2, fx is of order 2, fx is of order 2 means 10x 10x plus 5 plus x to the power 2, 10x plus 5 plus x to the power 2. This is the kind of a function I have. Let's remove the first order. 10x plus 5, just cut it down, only x square. So fx equal to x square, fx equal to x square. Can I reproduce in gx? So gx is asking fx, can you give me dual derivative? Because I am trying to reproduce you, can you give me dual derivative at x equal to a? Okay, leave the x equal to a fundamental. Can you give me dual derivative? Now, if it is going for dual derivative, then x to the power 2 becomes 2x and then it becomes 2. He is replying 2. Now, if you want to exactly reproduce the dual derivative, then equation is gx equal to d2 fx by dx square into x square. Gx equal to d2 fx by dx square into x square. So 2 into x square. But here it is x square, here 2 into x square. This proves that I have to divide by something. Let's divide by 2. Now it is same. X square, if I want to, if fx is a function, if I want to reproduce it as a polynomial equation of degree 2, then I am asking dual derivative. If I am asking dual derivative, it is x square, it is replying with 2. If it is replying with 2, then it becomes d2fx by dx square into x square. This is what Taylor is suggesting. So if that is that, then it becomes x square fx x square dfx x df square x by dx square df d2f by dx square x square. So it becomes 2x square. I divide by 2. It becomes x square. Now there is another fx is another function x to the power 3. X to the power 3. Now he is asking, gx is asking, can you give me triple derivative? Now it becomes 3x square, then 6x, then 6. It is returning 6. Now he is thinking that if I want to reproduce triple derivative, then my equation should be gx equal to d to the power 3 fx by dx cube x to the power 3. If I do so, then it becomes 6 into x to the power 3. But here it is only x to the power 3. So divide by 6. What is divided by 2 and divided by 6? Now I have to think. Now if it is x to the power 4, then it is asking for fourth derivative. then it becomes 4 into 3 into 2, and then 1. 4 into 3 into 2 into 1. So it is replying that it is 4 into 3 into 2 into 1. Now d to the power 4f by dx to the power 4 into x to the power 4. So that is gx equal to. Now it becomes 4 into 3 into 2 into 1 into x to the power 4. Now I understand that I have to divide by factorial of n. So if I have to replicate a function which is of polynomial x to the power n, then I have to get d of f to the power n by dx to the power n into x to the power n divided by factorial n. So each polynomial, one degree of particular polynomial, 1, 2, 3, 4, whatever degree it is, exactly I can replicate as gx when I have d of function f d to the power n of function f by dx to the power n into x to the power n divided by factorial of n. If I do so, then it is exact replica. Now consider this fx. This fx is full polynomial series to the power 0, 1, 2, 3, 4, 5, 6, everything. Then here we will add everything, whatever we have done. Now we will close fx. Fx is closed now. Fx is what it is, I don't care. Now gx, yeah, if I have to reproduce fx in gx, then I would say, can you give me the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, whatever it consider. Okay. Now it starts giving first derivative, second derivative, third derivative, fourth derivative, fifth derivative 0. There is nothing. I have polynomial till 4 degree only. This much you will get. Now he is making equation gx equal to dfx by dx x to the power 1 divided by factorial 1 plus d2fx by dx square x to the power 2 by factorial of 2 plus d to the power 3 fx divided by d to the power 3 fx divided by dx to the power 3 x to the power 3 divided by factorial of 3 plus d to the power 4 fx by dx to the power 4 x to the power 4 divided by factorial of 4. Okay, so this is called Taylor series. What is missing here? Missing here is if the dfx by dx, all the derivative is scalar value. It is not algebraic equation. Derivative can be algebraic at any point x equal to a. So if that is the case, then it converts into dfx by dx into x minus a plus d2fx by dx square x minus a whole square divided by factorial of 2 plus d3fx by dx cube into x minus a to the power 3 by factorial of 3 and so and so. So for any function fx, now I don't care what is fx. Can you see energy and mass creation? Einstein theory. If you have energy, then you can create mass and velocity. If you had mass and then energy, it will carry the velocity. So here fx, the net energy inside fx is all its derivative only. Otherwise, all are wasting, not required. That energy gx is fetching from fx and it is creating the full mass from the energy only. So this is mass to energy conversion. Now, for any fx, what is required to return? First derivative, second derivative, third derivative, fourth. Now fx has exponential, fx has sin x, fx has logarithmic, full. But gx is never asked, can you tell me what you have? Can you tell me first derivative, second derivative, third derivative, fourth derivative, whatever it is interested in? And then it creates a polynomial equation. What is missing now? Missing is the y-intercept. If I am talking about x differentiation at x equal to a, okay, then there is now any polynomial equation, any line equation when it passes through a point a comma b, then approximation will have to think about a equation that is y minus y0 equal to x minus x0, where x0 and y0 is a point through which the line is passing through. So y0, if I talk about where it is making, where fx is a line curve which is passing through a point called x0, y0 or a comma b. Same gx, then for a, I am thinking now it is x minus a. So everywhere x square, x to the power 3, x to the power 4, I replaced with x minus a. X minus a, x minus a whole square, x minus a to the power 3. Now what about the b? It is passing from a and b. B is nothing but fa. if if there is x-axis and there is a function over it, there is a point at a, it is touching the curve and it is called a comma b, then a and b can be said as function at a1. So now the net equation Taylor series, or I can say my series because I have invented this. Taylor's way of invention is different. So that we will talk. Actually, I invented this earlier. Later, I came to know this is already invented because we need this series when we go for like of maxima, minima, approximation. If I have two dimensional also, we'll talk about two dimension also. If I have two dimension, 3D, in 3D and those area, finding a surface, if surface is like this, then some point it will be a hill, mountain peak. Sometimes it will be a valley. Where it is a valley and where it is mountain peak, if I want to understand that, then I have to take any function as a second order algebraic equation. Then only I can think that it is maxima or minima depending upon the partial derivative 0. So I invented this way. This is my way of calculating any function at approximation in dual order. Actually, I tried dual order, now all order. Later I came to know this is already invented by one Mr. Taylor. Anyway, this is my way. This is how I had brought it. Now the gx becomes gx equal to y minus y0. The gx minus y0 means gx minus f at a, gx minus b. So gx equal to f at a plus f dfx by dx at x equal to a, x minus a, plus d2fx by dx square at x equal to a, x minus a whole square divided by factorial of 2 plus d3 f fx by dx at x equal to a, x minus a whole square divided by factorial of 3 plus d4 fx by dx 4 power 4 at x equal to a, x minus a to the power 4 divided by factorial of 4. Keep doing this. Just add f at a, fa at the beginning. Now this is exact. This is called polynomial approximation, because if it is also polynomial, then probably it will be exact way. Okay, like if I have fx equal to x to the power 2, fx equal to x to the power 2, then dx is equal to d2 fx by dx, x to the power 2 divided by factorial of 2 is exact match of this. If it is x to the power n, then dn fx by dx, x to the power n divided by factorial of n is the exact replica of fx to gx. But fx may not be this clean. Fx can be sin x, exponential, whatever it is. It is a black box. What is fx? I don't know. But I need fx in terms of some polynomial approximation, because I need to do some computation which is only polynomial I want. So consider that this is the fx. This is the fx. Uh, this is fx. Something. This is fx. Some equation. And this is point A and B. At this point, if I'm this is fx, this is gx. I want to replicate this. Now gx is saying, can you give me the single derivative at point A? So at point, this is point A. A and B. This is B, and this is in x-axis, this is A. This is A comma B. At this point, what is the derivative, single derivative? It's sent to gx. With that derivative, now gx form equation as gx equal to fa plus dfx by dx at x equal to a into x minus a. So this is the ultimate. But what is that? So that is, this is, fx is certainly, it is not a line. So if I ask for single derivative, okay, single derivative, then it is a tangent at that line. If it is a tangent at that point, but still at that point, this tangent and this, they have same height. So fx at a and gx at a are same. So this is highly used when we want a simplification of fx at any point a. We will see it, how simplification and those things actually matter. So this is a big deal. Now we will prove it as the way Sir Taylor, Mr. Taylor, he has proved his approximation of any polynomial, any equation fx to polynomial. So later we'll see Maclaurin series also.